Hello. Today is topic 1, section 13, further complex numbers. Okay, so write the complex number in polar form. Okay, so last lesson we learned a plus bi. We can graph that because a is our real number and b is our imaginary number. All right, so if we think about this as our triangle, well, our theta here, we can do some trig functions, okay? So we can do sine and cosine. So sine of theta is opposite over hypotenuse, right? SOHCAHTOA. So b over r. Well then, check out what b can be. We move the r over to the other side, and that's what we have. All right, if we do cosine of theta, oh, that's my dinner. Cosine of theta is adjacent over hypotenuse, so a over r. So we move the r to the other side, and lo and behold, a is r cosine theta. So if we want to write it in polar form, all right, a is r cosine theta, and b is r sine theta I. That's it in polar form. Okay? So here's all the notifications from Cognity. Okay? So oftentimes instead of writing cosine theta plus I sine theta, right? Because I guess I did write that incorrectly. We don't want to put it after the theta because you don't want to accidentally include it like that. Okay? So I really should have put that I here because it's after the number, right? But before the function. Okay? Right, you always leave that radical, log, sine theta, all that stuff always is at the end of your expression. Okay. All right, so shorthand is just writing it as r cis theta. So that's cosine I sine. Okay, so that's just a shorthand, and that's how I'm going to write it. Okay, so here we want to write this in polar form. Well, we need to do a few things, right? First, we need to find r, and r is just another word for our modulus. So we're going to take the square root of 3 squared plus our negative 2 squared, so it's the square root of 13. So that represents our r. Then we need to get our angle. So if you remember, that was our inverse tan of our y over x, so negative 2 over 3. All right, we plug that in. Let's see, we get negative 0.588 if we do 3 sig figs. Okay, so that represents our angle. So here we have our r and our theta, so then we can just write it as r cis theta. So the z here is going to be the square root of 13 cis our angle, negative 0.588. There you go. Now you can write it as square root of 13 cosine negative 0.588 plus I sine negative 0.588, but that's just longer. Okay, go for it if you want. Okay, so that was polar form. There's also Euler Form. Okay, I know it looks like Euler Form, and I really want to say it every single time. I might even slip up, and I hear Euler. I don't know. Anyway, so Euler's form is exponential form. Okay, so it can be written as r times e to the I theta. Okay, so in case you wanted to know, a little backstory. All right, around 1740, that's when they started getting into imaginary numbers, and then they started realizing that when you square an imaginary number, it's negative, right? So Euler started playing with the Taylor series, and I'm not the best at describing this stuff. I don't teach calculus, so I thought this was the coolest or the simplest explanation I could find on the internet. So hopefully you remember the Taylor series from calculus. Anyway, this is just how it broke it down. The whole idea is that e to the ix is represented as cosine as the real parts, and sine is the imaginary parts. Okay, that was the whole idea of what he was doing. So let's write this one in Euler form, so exponential form. So first we need to find the modulus. So that's the, get my pen working, the square root of 25 plus 1, so that's just the square root of 26. And then we can find the angle, so the inverse tangent of 1 over negative 5. We get, what is that, negative 0.197. Oh, I think I misspoke earlier. I didn't mean degrees. We're going to use radians. Okay, that's what we're going to be, because usually we don't have to write a unit with radians, but degrees, you write the degree symbol. So again, lazy factor, use radians. Okay, so here we've got our angle and our modulus, but I want to talk about this one a little. Okay, if we were to graph that on the imaginary plane, right, we would get negative 5 plus 1, we would be over here. However, if we were to graph that angle is going to be down here. This angle is negative 0.197. So it's not matching up with what I want. Okay, so I always recommend that you should draw it. Okay, whenever I taught pre-calculus, the biggest hint I've ever given anybody is make a picture. Make a picture, make a picture, make a picture. Actually, I say that in statistics all the time too. Okay, so this doesn't line up, so we need to fix it. Okay, so how do we fix it? Okay, hopefully you were thinking, well, that's 180 degrees, which what we're in radians, so we're going to say pi. So we're going to take pi is from here to here, right? So we want to subtract this angle, because this is the same as this angle. Okay, so pi minus 0.197. So pi minus 0.197 is going to give me my angle, which is 2.94, and let's see. Okay, so now we've got our angle and our radius, so we're going to write our number, and sorry, I can't find my words. So the square root of 26 times e to the 2.94i. Okay? You don't have to put this multiplication symbol here. I like to, just so you can see the separation in the radical. Okay? I don't want you to accidentally mistake any of that being underneath it. Okay? So I just like to be super clear on how I'm writing it. Okay, so now we're going to work backwards. So we're going to write this in Cartesian form. Okay, so going back. So remember, 2 is our radius, and pi over 2 is our theta. So if we're putting it back into Cartesian form, maybe it might help you to think of it in r cis theta. Okay, so that would be 2 cis pi over 2. So that's 2 cosine pi over 2 plus I sine pi over 2. And hopefully you remember cosine of pi over 2 and sine of pi over 2, okay, from your unit circle. I use the hand trick in case I ever forget. If you don't know the hand trick, I'll be happy to show you. Just let me know. So cosine pi over 2, that should be 0. And sine of pi over 2 should be 1. So our answer is just 2i. Fancy, I know. All right, let's see. So here's a chart that you can practice on your own, going back and forth from Cartesian to polar to Euler's form, back and forth. You know, kind of practice it, see what you can do by hand. You can also do this by using your calculator. So I recommend you try this by hand first, see if you can go back and forth, and then test it with your calculator. So how you can do that is, I don't know why the chart had this, but it should have been 2 plus 3i. That's how I would have written it. So 2 plus 3i, so second dot. And then you're going to go, I believe it's what, math, and where is it? There we go. Okay, of course, we're in the complex section. So go down to polar, and here we have it. So let's see if you did that by hand. Looking, here we go. Let me uncover this. Okay, so, well, they of course give it to us in decimal form, but here you have, what is that, 56? I believe that's in degrees. Yep. So then you just convert that to radians, which we'll get to that later. But this is one way. It's not the best way, but you can always check it by doing, what is that, the square root, where's my button? Square root of 13, we see that is 3.6055, right? So we know we did that correctly. And then we can convert our degrees to radians. Let's see. Okay, so here's the answers to your chart. So hopefully that makes sense going back and forth, okay? All right, it really helps to know the unit circle. Again, I've got a hand trick. You gotta know. Okay, so let's see. Write the complex form in a plus bi form. Okay, I think we've done enough practice with this. Again, make sure you, pay attention to your angles and all that. Let's see. So putting it in polar form. Here we have what happens when you multiply two of these. Okay, we're going to multiply the modulus, so multiply the radii, and add the angles. Okay, so here we multiply. So we're going to multiply the modulus, so we get 4 square root of 2. And then cis theta, we add the angles. So I'm going to rewrite them with 12. So what is that? 9 pi over 12 minus 2 pi over 12. So it's 4 square roots of 2, cis 7 pi over 12. Okay. And there you have it. If you weren't, let's see, I shortened it because it did the conversion. If you did the conversion with the decimals, it's fine. Then it would have just been a decimal here. I think it was, what, 1.83? Okay, that's fine. Oh, I guess I didn't show my answer. But yeah, so see, they did it as a decimal. Okay, so what happens when we divide? Lo and behold, same thing you think. We divide the radii, and we're going to subtract the angles. Okay, so it's because the angles are, inside that function. They're inside the exponent. Okay, so I think they do a little things a little different. Okay, so for this one, if we divide w and z, we put it in polar form. Okay. So let's see, we're going to multiply the modulus, so 3 times 4, and our new one is 12. And for our new angle, we're going to take we're doing w over z. So make sure you're doing the subtraction right. It's the top numerator over the denominator. So I would not start with this one. I would do w over z. So the angle for w is negative 0.172. And then I subtract this angle from z. So 2.17. And that gets me negative 2.34. Remember, polar form is this form, so it's going to be 12 cis negative 2.34. Next one. So consider this, convert it to polar form, and then divide. So take a second, convert those. Okay, maybe pause the video. Okay, so hopefully you got this when you converted. Now when you convert to, or we already converted to polar form, so now we're going to divide z1 over z2. Okay, so I'll let you guys do that. Again, oh well, that's not so hard. We can just multiply square root of 2, and then we subtract the first one, so negative pi over 4 minus pi over 6, that is negative 5 pi over 12. That's surprising. Hopefully not, because that's actually in the next section, or this next part of the question. Okay? So we want to find the exact values. Okay, well think about what we just did. We divided it when it was in polar form, but it was also in complex number form. Couldn't we have just left it at that? What if we had done z1 over z2, but we used 1 minus I over the square root of 3 plus I? So then we do some converting. All right, we multiply by the square root of 3 minus I, square root of 3 minus I. So when we do that, we end up with the square root of 3 minus I minus the square root of 3I plus I squared all over 3 plus 1. Alright, so what if I put the imaginary stuff together and the real stuff together? So we'd have the square root of 3 plus 1 minus I square root of 3. I just need to put that radical second. It's going to drive me crazy. All over 4. So separate it. This is your real part. So square root of 3, or 1 plus the square root of 3 over 4. Since these are both negative, I'm just going to put a negative fraction. And I get I plus I squared root of 3 over 4. But take that I out, and now you're going to be blown away. Oh, what am I doing? Put an equal sign. I just like to put them like everywhere, I guess. Uh-oh. There we go. It was not working for me. All right, I. So we pulled the I out. So now we've got the real part and the imaginary part. Well, hopefully you remember that cosine was the real part and sine was the imaginary part. So the exact value of cosine is actually 1 plus the square root of 3 over 4. And the exact value of sine is negative 1. Well, I mean, I guess you're right. I guess Cognity wrote it as a plus sign there and kept this as two negatives. So it's negative 1 minus the square root of 3. Don't normally put the negative out there when you have too many things up there in the numerator. What can I say? All right. Any questions? Feel free to ask me in class. Okay, so here's another example. So here we're going to go the other direction. Okay, so here we're going to find z cubed in a plus bi form. So instead of doing what we did last time and doing 2 plus 2 square roots of 3i and then cubing it, right, we could write all that out, all right, but we want to try Dwarf's theorem. Don't know if I'm pronouncing that correctly, but what we do is we want to convert it to polar form first. Okay, so first we need to find the modulus. So we take the square root of 2 squared plus 2 squared of 3 squared. That gets us 4. We do, to get the angle, the argument, we're going to do the inverse tangent of 2 square roots of 3 over 2. So that's just going to give us pi over 3. So in polar form, this would just be 4 cis pi over 3. All right, now Dwarf's theorem says if we're going to raise z to a power, okay, we're also going to raise the modulus to the same power. So if we're going to do z cubed, then what we do is we do 4 cubed, and then we multiply by the angle. So we're going to do, since we raised it to the third power, we're going to do 3 times pi over 3. Hopefully that's making sense. So this would be 64 cis pi. So that's just 64 times cosine pi plus I sine pi. And hopefully we remember at pi, this would be negative 1 and this would be 0. So 64 times negative 1. So our answer is just negative 64. All right, yes, there's a lot of steps and a lot of calculations, but I feel like I make a lot less mistakes doing it this way than doing it this way. All right, but that's how you show that theorem. Okay, so here we want to write it in polar form. Okay, so the first thing I would do is convert the top and the bottom to polar form. Okay, so 1 plus I into polar form, so you should get the modulus to be the square root of 2, and you should get the angle to be pi over 4. Okay. And so let's see, so that the numerator is going to be square root of 2 cis pi over 4. Now convert the denominator. So 1 minus I we convert that first. So the modulus would be, again, the square root of 2. And your theta, the inverse tangent of -1, so what's that, negative pi over 4. Ooh, what am I doing? Get that a little nicer. Alright, so this is going to be the square root of 2 cis negative pi over 4. But we need to raise that to the 5th power. So we're going to do, let's see. So the numerator is, let me write it as this. Okay, square root of 2 cis pi over 4. The denominator, we need to raise it to the 5th power. So we do the square root of 2 to the 5th. And we multiply, so we get negative 5 pi over 4. Right? You raise it here, and you multiply with this one. Alright, and then since we're dividing, okay, we can just straight up divide the radius, or the modulus, whatever you want to call it. So that just eliminates one of the square root of 2's. So we end up with the square root of 2 to the 4th power. And then cis, we take, since we're dividing, we do pi over 4 minus negative 5 pi over 4. So we end up getting, is that 1/4 cis 6 pi over 4, so 3 pi over 2. Is that, I'm hoping that's making sense. Of course, just like with any problem you do in pre-calc or with trig, you're going to have to check and make sure that your angle makes sense. So in this case, our angle is 3 pi over 2. So we start here, remember, 3 pi over 2 is here, but our answer should always be from negative pi to pi. Alright, so we need to be within this range. So we went too far. Okay, so instead of going to the left, let's go this direction and find that. So that's going to be negative pi over 2. So we should put our answer in that form. So really our answer should be 1/4 cis negative pi over 2. Okay? Alright. Okay, so this was a similar example. Okay, I think you guys can do this one. Let's go to the next one. Okay, so it's very important to understand how to move your angles around, okay? Okay, so here's your graph, and let's say z is the nice little a plus bi. So let's say their a and b is both positive. So let's just say z is nice, it's right here, okay? I guess here, I'll put it in coordinate form, so a comma b. So when we do negative z, right, that's negative a minus bi. So that's over here now, negative a, negative b. Well, think about what you just did with your angle. All right, here, let me try and do this. All right, so this angle here, and you have this one here. All right, what you've done is you've added pi to that angle because this is the same as this. So that's what you're doing here. You're adding pi to the angle if you do the negative of your complex. All right, when you do z star, I guess, that's called the conjugate, so that's going to be A minus BI. So A minus BI is going to be over here. So that's A and negative B. So when we do this, okay, this angle, I know, I did not draw this to scale. Okay, so what we've done here is we take 2 pi minus that angle, okay, because we always write it as going from here around, okay? So that's why in the green we do 2 pi minus the angle. I just think this helps to visualize it, okay? So let's do the negative of the conjugate. So that's just negative A plus BI. So that's going to be over here. Negative A plus B. So where that angle, it makes the same. So there you're going to do pi minus the angle. So it doesn't, the IB booklet's not going to give you anything about this. So that's why I think it helps to visualize it as a complex number and graphing it. Okay, I'm all about pictures, pictures, pictures. Okay, so determine which vector in the diagram shown represents each one. So let's see, I'm going to make these stand out a little bit more. So here we have Z1 and Z2. Okay, I don't know why I erased it. Let me change my pen. Okay, so let's just call these some arbitrary numbers. So negative A and B, because I went left and up, and this one I went left and down, right? So if I'm adding the two together, I'm adding these values, negative A and negative X. Okay, if I'm adding the Y's together, okay, so if I'm adding the X's together, that's making it longer, so it should go further to the left. And if I'm adding the Y's together, well, really it's the difference here. Okay, so C is going to be A. Okay, that vector represents A. All right, then we think about negative Z. So negative Z would be positive A and negative B. So the only one that's at a positive A, negative B is B. And if we do Z2 minus Z1, so negative X minus the negative A, so adding the A value. Sorry, I'm thinking about the Y's. Okay, so negative X, and I'm adding that A value there. So I'm kind of going inwards, right? And if I add these two together, my Y's, this little bit and this bit, oh, I'm sorry, I keep saying adding, we're subtracting them. So negative Y minus B, that's going to make mine go further down. So this should be D. Okay, because we're doing negative X plus A. So this got a little bit shorter. And our Y value was negative Y minus B. So our Y got even longer because we went further down. Hopefully that makes sense to you. If not, you know. Okay, so given that W is R cis theta and Z is M cis mu, I don't know what that is. Find W, Z, and W over Z. Okay, so hopefully these are pretty easy to answer. Okay, so that was just doing our basic formulas, right? R times M, add the angles. R divide by M, subtract the angles. Okay, so what does that mean? Okay, well, if we did R times M, we've made it bigger. Okay, we've stretched it by a factor of M. Okay, so that's what z is doing to the w, or doing to w. Okay, so it's stretching by a factor of m, and it's rotated anti-clockwise. Okay, think about that. Anti-clockwise is going, well, clockwise is like this, so anti-clockwise is that way, which is how we do angles. So when we add an angle, we're going in that direction. All right, when we divide, we are compressing it. Okay, so we're stretching it by a factor of 1 over m. We're making it smaller, and we're rotating it clockwise. So we're subtracting an angle, so now we're going in the other direction, clockwise. Okay? Example 4. Okay, so determine which of the vectors in the diagram shown is the most appropriate representation. So if that's z, I'm going to multiply the modulus by 1/2, so it shouldn't be nearly as long. And the angle, I'm adding pi over 4, so I should be going anti-clockwise, and it should be half the size. So halfway, moving that direction, has got to be b. All right, the next one, we're dividing by 2/3. Okay, so we're dividing by a factor of 2/3, so it's stretched by a factor of 1 over 2/3. That makes sense? So it's the flip. So that's actually making it a little bit longer. So it's going to go this plus some. All right, and we're going to subtract pi over 2, so we're moving in that direction. And pi over 2 is a right angle, so that should be d. Okay? Okay, so this is kind of working backwards from thinking about your trig functions if you were graphing them. So now we can think about them in polar form, and what I mean by that is we're breaking it into the real or the imaginary parts of the polar form, because a sine function is just the imaginary parts of polar. Cosine is the real parts. So here, since it is sine, all right, we know it's got to be the imaginary part of our cis function, where r is 2 here, and then cis of 3x plus 1. That's it. Okay, there's no work to be shown here, but this is the idea behind it. It's the imaginary part of your polar expression. Okay. Okay, so I know this was a very heavy topic. I know it took me nearly 40 minutes to get through, so please let me know if you have any questions. I'm sure you will. I'll be in class waiting.